Hi dears, today we can see some results on singularities in complex analysis. So first we can see what is singular point. A point Z naught is called the singular point if f of z is not analytic. Sorry. F of z is not analytic, but every neighborhood of z naught. But every neighborhood of z naught contains at least one point in which f is analytic. So if we see this is the function in which this is z naught and the remaining points or z1, z2, etc. z in the neighborhood is there. So in this point, the FZ is not analytic. It is fails to be analytic, but the neighborhood of the Z naught, we can see at least one point. At least one point, if is analytic, then we can say this particular point Z naught is said to be the singular point. Okay, so the condition is if Z is not analytic, but in the neighborhood the function is analytic. That is, that point is singular point. So here we can see that the types of singularity. So there are two types of singularity is there. One is isolated singularity. The second one is non-isolated singularity. So here you can see isolated singularity. The isolated singularity, there are three types, that is removable singularity, pole and essential singularity. Easy to find problems using these steps. That is limit z tends to a fz. If that value exists and it is finite, then we can say that is removable. Or you can see the second one. Some function has principal part. Principal part means that you can take from the Lorentz series expansion. So this is Lorentz series expansion. This is summation n equal to 0 to infinity a n z minus the whole 4n plus summation b n divided by z minus z, not the whole 4n, where this part is said to be the regular part and this part is said to be the principal part. So if a function which contains no principal part, there is no principal, that is the denominator which should not contain z term, then we can say there is no singular principal part. So if it's so, then we can say that that function or that point is said to be the removable singularity. So if you take the poles, the limit will be equal to infinity. That is the limit of the function. If you apply, you are getting 0 by some value divided by 0, that gives infinity. So and the second, you can see that if there consists of finite number of principal parts, that is if there are consist of finite number of denominator z parts, means also that is poles. Then essential means limit z tends to a f that does not exist, and there are infinite number of principal parts. For example, infinite number of principal parts means 1 divided by z square plus 1 divided by z cube, then 1 divided by z power 4 plus etc. So you can see that principal part means the denominator should be contains z. So here you can see infinite number. Then certainly you can say that that is belongs to the essential singularity. Finite number means 1 plus z plus 1 plus z square. Up to this it finished means then we can say that it is pole, because it consists of principal part in the denominator with only finite terms. Okay. So easy chart to remember this isolated singularity. So this is Lorentz series expansion. Now we can, and in the description box I am providing the link for the singularity which consists of more problems I practiced there. Please look after there. Now we can see the results. Let f be a bounded and analytic function in the deleted neighborhood 0 less than modulus z minus z naught less than delta. Then, so the condition is f is bounded and analytic, then either fz is analytic or fz has a removable singularity. So if it is bounded and analytic, then you can say it is analytic or it may be removable singularity. The second result, if fz be an analytic function in a deleted neighborhood of z naught and z naught is a limit point of zeros, then we can say that fz has essential singularity or fz is identity equal to 0. So the condition is fz is analytic function and z0 is a point, limit point of the zeros, then you can say it is essential singularities and fz is identically 0. So while studying, you can refer this to first result and the second result and see the similarity. Now you can see the third result, a limit point of the poles of the function. Limit point of the poles of the function is a non-isolated essential singularity. One of the important result, limit point of the pole, that is a non-isolated essential singularity. Then the fourth result, if fz is an entire function which has no singularity, analytic function, entire analytic function which has no singularity at infinity, then you can say that that function is a constant function. That function is a constant function. So the condition analytic and it has no singularity at infinity, then we can say that that function is a constant function. Now we can see residue, how to find residues. So if it is a simple pole, that is pole of order 1, then residue is equal to limit z tends to a z minus a into fz. Then the second one, if the function looks like this polynomial pi of z divided by z minus z a the whole power m means that the residue you can find as pi of m minus 1 dash of a divided by m minus 1 factorial. If pole of any order, then the residue is equal to 1 divided by 2 pi I integral over c fz dz. This you can see later in the residue theorem, that is integral over c fz dz, that is equal to 2 pi I into residue of fz. Then if it is a residue at infinity, then it is minus negative of this is z tends to some point, this is z tends to infinity, then negative of 1 divided by 2 pi integral over c fz dz. The next one, if n is a pole of order, n, then a residue z tends to a fz is equal to, that is order of pole is n, then 1 divided by n minus 1 factorial limit z tends to a d power n minus 1 divided by dz power n minus 1 z minus a the whole power n into fz. Again, if fz looks like two polynomial, that above and below, numerator and denominator would consist of a polynomial, and it has a simple pole of order a, then residue z is equal to a equal to pi of a divided by psi dash of a. So in the description box I provided the residue a link also. There I work out more residue problems. Please look after that. Now we can see the residue theorem. So let fz be a single valued analytic function inside and on a simple closed curve, except at the singularities like z1, z2, etc., etc. inside C. Then the residue theorem state that integral over c fz dz is equal to 2 pi I into summation, that is sum of the residues. That is residue theorem. So fz analytic inside and on a, if it is outside, then that is equal to 0. So inside and on a simple closed curve, then we can write 2 pi I into sum of the residues. Then the seventh one, the order of the zero of the polynomial equals the order of the first non-vanishing derivative. So order of first non-vanishing derivative means the derivative. First derivative will be not equal to 0. Of that function will be not equal to 0. So order of 0 of the polynomial equals order of first non-vanishing derivative. Then we can see the argument theorem. Let fz is analytic inside and on a closed curve C except at the finite number of poles or finite number of singularities. Then 1 divided by 2 pi integral over C fz is equal to n minus p. So n represents the sum of the multiplicity of the zeros of function fz, and p represents the sum of the multiplities of the poles of the function fz. So argument theorem, number of zeros minus number of poles in terms of sum. Then Cauchy's theorem, let fz and gz are analytic inside and on. For all this theorem, residue, argument, Cauchy's, the point you have to take is inside and on, the simple closed curve, and the condition is given here, mod plus g less than mod plus f. then you can say that f plus g and fz has finite number of zeros. So if for example in the question given fz is equal to a log polynomial z power 6 plus z cube plus 1 means you can choose that g of z is equal to z cube plus 1 according to this condition. Check this condition whether mod plus g is less than mod plus f. Then we can say that f plus g and fz has same number of zeros. So here it has 6 number of zeros means f plus g also has the 6 number of zeros, like that we can say. So then open mapping theorem, a non-constant analytic function on a connected domain maps open sets into open sets. That is non-constant analytic function. Thank you.